There you are. Okay. Sorry, I'm new to all this online teaching stuff. So there we go. Okay. How's that? Is it sharing now?
Yeah.
Great. Okay. Sorry, during the end of the regular semester, I was doing asynchronous classes, not synchronous classes, because my wife was teaching. So I have to try to figure all this stuff out as we go. So hopefully we won't have too many technical difficulties along the way. So life will be great. So as you know, we're going to meet every day. So from 9 to 10:15. Again, I'll record all of these videos and post them onto YouTube. So in case you can't actually join, then they'll at least be posted there. And yeah, so then I'll also post the link on Blackboard, so you'll be able to find your way to there from Blackboard. I'll show you where all that stuff is going to be. So first things first, so let's talk about the book. So we're using the same book that you used in 175, so that's going to be the G and Coley book. Now again, you don't need a physical copy of the book, so if you have a physical copy of the book, great. Otherwise, you can have, when you buy the rates for the homework system, you can include the e-version of the book, so you can actually just use it there. Or, I don't know if Dr. Merlot or anybody else told you, you even need a copy of the book. Pretty much any college physics book will work. They all basically say exactly the same thing. We'll be doing the Pearson Mastering Physics. So make sure you do the Pearson My Lab and Mastering. That's where you'll find all the conceptual questions and homework questions and etc. So this portion here, so where it says Greenwood 30303, that is the code you'll need to be able to sign up for this particular course. So we're having 5 exams, so let's go to the grading section. So basically we're gonna have 5 exams, but I'm gonna drop your lowest exam. So throughout the semester, actually 2 weeks from today will be your first exam. So we'll have 5 regular exams, and each one of those exams, again, will be worth 100 points. So that'll give you a total of 500 points, but again, I'm gonna drop your lowest exam, so that'll be 400 points. For the semester. Homework, I'm going to do something a little bit different. So homework-wise, this is something I've been doing in my 206 class. Homework for now is only going to be optional, which basically means it's not going to be mandatory. So you will have homework assignments. I'm going to post up bulk homework assignments for you to view. But for now, they are not going to be required homework assignments. So basically, the idea is I will post pretty much per chapter, depending on the size of the chapter. So this first chapter we're going to go through, chapter 11, is pretty long. You have multiple different topics, but I'm going to post somewhere around, say, in this case, it's going to be about 22 different homework problems. But again, they're not going to be mandatory. So the idea is that I would like you to kind of work on them, do a few of them, kind of get better acquainted with the topics that we're actually talking about. But I don't want you to spend a huge amount of time basically working on the homework. So basically the homework will be there to kind of give you practice on working on these problems, but I'm also going to post old exams, and we're going to be doing a lot of group work basically in the class. So you'll have group assignments. So I'd rather have you spending more time on those, the group work, as well as the old practice exams, because those are going to be a lot closer to what you're going to see on the actual exams themselves as opposed to the homework. So again, the homework is there basically just for practice, kind of become more acquainted with the topics that we're actually talking about. But for now, the homework will not be mandatory. But there's a caveat to this. And the caveat is that if people are not doing well on the exams, then I will make the homework mandatory from that point on. And then it'll actually count for the rest of the semester. So as long as everybody's pretty much doing well with the exams, then there is no real need for pardon me, for the homework to be mandatory. So again, for now, homework is just going to be optional. So again, I'd like to see you work on a few problems, just kind of become more acquainted but again, spend more time kind of working on the group assignments as well as the practice problems that I'm going to post as well. So having said that, so for now, again, the homework will be worth 100 points if necessary, but for now the homework won't be mandatory, so that actually won't be worth anything. So we have lab. So lab is going to be 125 points. Now, I'm sure you know this from 175, but it works exactly the same way in 176. So lab portion will be a separate grade, but its actual grade will be used as a component of the lecture course. So that's going to be worth 125 points. And for you to pass the lab as well as the lecture course, you have to get at least a 70% or higher in the lab portion. So again, same thing with 175. So if you get below 70% in the lab, then you automatically fail both the lab and the lecture, even if you have 90s on every exam. But I don't think I've ever had to do that before, so you don't have to worry about that. So in-class points, these are going to be a mixture of, again, the group assignments that we're going to work on, and then basically whatever participation. Now, again, I know that not everybody's going to be able to make it to every class during the live stream, so that'll be mostly just looking at the group assignments. And I'll talk more about the group assignments in just a second. Last part is going to be conceptual questions. So conceptual questions will again be on mastering physics. Those will be mandatory. That's going to be 50 points towards your final grade. And those will be posted 3 times a week. So I'm going to post them on Mondays, Wednesdays, and Fridays, and they'll be due the following day. So basically I'll post them and you'll have about 24 hours to get them done. So I'll post them on Monday, again, Wednesday and Friday, and then you'll have about 24 hours. So they'll be due on Tuesday, Thursday, and Saturday. Those are mostly going to be conceptual questions, misconceptual questions, things like that, to try to test your understanding of what it is that we're talking about throughout the course. So let's go back to group assignments. So group assignments will be, again, for participation, but they're also going to be used as extra credit on the exams, which basically means that when I post these group assignments, I want you to continue working on them outside of class as well. And for each one that you turn in, you'll get a point of extra credit. So typically we'll have about 5 to 10 of them per exam. So it's pretty much about 5 to 10 points of extra credit I'll give you away for free just for working on these group assignments. So they don't have to be correct. They don't have to have exactly the right answer. I just want to see that you're actually working on them. So as long as you're working on them and you turn them in, you'll get a point of extra credit just for turning those in. Now, if you're working on them with a group of people, so if you Zoom with somebody else and you're gonna work on those together, so just give me 1 copy. That would be fine. Just make sure everybody's name on it, so it doesn't have to, you don't have to turn in all of them if you're working in a group. So I'll skip down to here, basically the schedule. So there's no class this Friday, so that'll be for the 4th of July, so we won't have class. But other than that, we meet, again, every day for the next 7 weeks. And so every day for the next 7 weeks. And as you know, summer classes are always very intense. Physics itself is pretty intense. So we're going to move at a very rapid rate. And again, basically seeing each other every day over the next 7 weeks. It goes by pretty quick. So again, we have 5 exams. So 2 weeks from today, we'll start our first exam, and then basically every week after that, we'll have an exam all the way through the end of the semester, where the last exam will be on this last day of August 14th. Again, 5 exams, we'll drop the lowest exam, so if you do really well, exams 1 through 4, then you don't even have to take exam 5 if you don't want to, if you already have a high enough grade that you can just use that as your dropped exam. There will be no final exam. Something else I should talk about. So basically just 5 regular exams, no final exam. I don't believe in doing final exams over the summer. It's just too compact as it is. So the way it works in the summer is basically every 2 days that we meet is equivalent to 1 week of regular semester classes. So again, it's intense. We're going to go through a lot of material in a short amount of time. That's another reason why I'm not making the homework mandatory. I don't want to beat you down too much with doing all that kind of extra work. So let's talk about the exams for a little bit. So let me bring up my Blackboard here. So basically, here's the home page for Blackboard. If you come under here under course contents, this is where you're going to find the exams. So basically, on the day of the exam, you'll come onto here. You'll come onto this tab where it says exam here. And then you'll find a link for whichever exam that we're actually working on. So let's say that's exam number 1. So when you click on there, you're going to find the exam. So at 8:55, the morning of the exam, so for example, 2 weeks from today, you'll find the first exam. And then there'll be a slew of different submission links that you'll click to upload your material. So I'm just going to upload the exam, and then you will basically on blank paper, do the exam on the blank paper, either scan it or take pictures of the exam, and then upload those pictures basically directly onto Blackboard. So for each one of the different questions, you'll just upload that particular picture for that particular question right onto the link. And then the same thing with outside of extra credit. So I'll also assign extra credit for each individual exam, as well as the pictures of the group assignments, which again, you'll get a point of extra credit for each one of those that you submit. So there'll be a lot of extra credits at your disposal throughout this semester. Now, typically people who make it from 175 into 176, they do much better in 176, just because they pretty much already know what's going to happen from 175. You know what needs to be done. So typically the DWF rate for 176 compared to 175 is much, much smaller. So almost everybody who takes 176 passes. So it has a very, very high success rate to it. So any questions on the syllabus? So anything that I talked about with grading, submission, all that kind of different fun stuff. No, everybody's okay? And if I get talking too fast, just let me know. Sometimes I just talk fast.
Will the homework be on Blackboard, or will it just come up in my Pearson?
Oh, the homework will just be on Pearson, so it won't show up on Blackboard itself. And the bulk assignments are always going to be due the night before the exam. So for example, again, our first exam is 2 weeks from today, so 2 weeks from yesterday would be when those bulk assignments are due. But again, they're not, they're being graded on Pearson, but the points are not counting for anything as of yet. So again, we're making the homework optional at this stage. But again, the conceptual questions will also be on Pearson itself, not on Blackboard. Pardon me, but those will be counted. Those will be graded directly on Pearson. But again, those you only have about 24 hours to do. So they're typically going to be due at about 5 o'clock on the next day. So again, if I post conceptual questions today, then they'll be due by 5 o'clock tomorrow. Any other questions on? Okay. So let's talk a little bit more about this class. So this class is kind of a strange and interesting class. So we're going to start off again in more of the type of physics that you saw from 175. So things that are moving, things that are motion, Newtonian type physics. And that'll basically be the subject of our first exam. So we're going to talk about some of the things that you've already seen in 175, and that's primarily springs. So we're going to talk about springs more in depth. What are they? How do they actually work, etc. From there, we'll move into waves, looking at primarily sound waves and other type of waves like mechanical waves. And then we're going to jump after the first exam into now the bulk of what we're going to do the remaining in the semester, which is electricity and magnetism. So electricity and magnetism is a little bit different because we can't really conceptualize what we're actually doing. So when you think about 175, you can conceptualize things that are moving, right? You can think about a ball which is being thrown, being rolled across the ground, things that are moving, etc. So these were macroscopic things that you could actually conceptualize and that you could see. But in 176, again, by the time we get to electricity and magnetism, we're talking about microscopic particles, mostly electrons, protons, things like that, that we can't see. So our ability to conceptualize and our intuition that we have in 175 is not going to be there when it comes to 176. So we're going to have to rely a lot more on our fundamental basics, things like conservation of momentum, conservation of energy, et cetera, as well as the math to really kind of understand what's actually happening. So we're going to lose some of that intuition and have to rely a little bit more on the math, but in my respect, I think it's a lot more interesting when we actually think about things like electrons and things that are actually moving around and how these things actually work. Now, by the time we reach the end of the semester, we'll be back into waves, talking about light and electromagnetic radiation. So all the things that we're going to see at the beginning of the semester are going to come back to us at the end of the semester, and we're going to have to rely on all those things. Now, the other thing that makes this class kind of strange is that it builds upon everything that you did in 175. So everything that you did in 175 gets carried over into this semester, and we're going to move forward from there under the basis that you remember everything that we did in 175. Now, not everything we did in the 175, you don't have to worry about things like thermo for the most part. I might talk about it every now and again, but we don't have to remember all the things from thermo. But most of these things that we've done, again, especially the big principles like forces, conservation of energy, conservation of momentum, torque, all that stuff, we're taking as all of you remember that, and we're going to start building on it from there. So I know some of you are coming from Dr. Merlot's 175 class, but for those of you who aren't, how long has it been since you've done 175?
I did 175 in the spring, so it's not been that long.
Okay. So most of you coming from spring or summer doing 175, or has it been a little longer for some of you?
I took 175 in the fall.
Oh, in the fall, okay. So it's been a little while. Gotcha. Okay. Well, make sure you make an appointment with me if you're, to go back to those things if you're having a little bit of difficulty. Okay. So any refresher that you need, just make sure that we work on that. What about the rest of you? Everybody else last semester or so?
Last semester for me as well.
Okay.
Same here.
Okay. Very good. Okay. So, good. So again, here's the Blackboard page. So here's that. I guess I don't need that right now, so we'll get off of that. All right. Sorry about all my hundreds of thousands of windows here. We'll figure it out as we go through. One other thing I should tell you, I think I put this in the email. I have 2 small children at home, so every once in a while a child might come busting in the room. So don't be alarmed if that happens. We'll kind of work our way around that. All right, so we've gone through all that. So let's go ahead and start talking about new stuff. So again, the first part of this chapter, we're going to start chapter 11, is we're going to start looking at something you've already seen in 175, but we didn't talk too much about it, but you used it a lot, which are springs. So primarily simple harmonic oscillation. So what is simple harmonic oscillation? So simple harmonic oscillation is a motion that repeats itself basically indefinitely. So particular examples of simple harmonic oscillation, and why aren't you coming back up? Oh, it's right down here. So particular examples of simple harmonic oscillation are things like spring mass system. So here I can have a spring and a mass, attached to it. It will be harmonically oscillating back and forth. As long as there's no friction, this thing is going to oscillate back and forth indefinitely forever. Another example of a system would be a pendulum. So this is simple harmonic oscillation. Here I displace it. This thing will then oscillate back and forth forever. Again, assuming that I'm in a vacuum and that there's no friction. So another example would be, again, a pendulum. Other examples are things like solids. So for example, if you think about a solid like a table or this pen or anything else, it's made up of atoms. Those atoms are in a lattice, and inside of those lattices, we have atoms which are basically oscillating. So those things are simple harmonic oscillators as well. So we can put on here a lattice. Other things are, for example, an electron which is orbiting a proton. So in that case, we have, if you think about Bohr's planetary model of an electron, here the electron is orbiting around the proton, which is also simple harmonic oscillation. Oops. Go ahead. So here we can have, again, so a hydrogen atom. Oh, I don't know how to spell. Hydrogen, there we go. Atom. Also, for example, the moon, when the moon orbits the Earth, it does that in a regular 28-day cycle. So that's also harmonic oscillation. So, whoops. So no technical issues. There you go. So here are the moon about the Earth. So these are all particular examples of simple harmonic oscillation. So hopefully you can kind of get from this list that pretty much almost everything in nature somehow falls under simple harmonic oscillation. So simple harmonic oscillation is one of the most important, one of the most fundamental ideas that we can actually have in physics, because it's something that occurs all the time. And actually the way we do physics in reality is that systems that we actually can't solve, we turn it into a harmonic oscillator and we actually solve it that way. So it actually shows up all the time, even in things that actually aren't simple harmonic oscillators. So basically what we want to do is we want to start going back to the idea of simple harmonic oscillation and start looking at it further. So the first thing we're going to start looking at is, again, something that you know from experience, but this is what we call Hooke's law. So we want to talk about, again, a spring. So let's say I have a spring and I want to grab onto the spring here and I want to pull it, right? So if I start pulling on the spring, what's the first thing we notice? So does the force that we have to apply to the spring to get it to move, does that increase, decrease, or stay the same as I try to pull the spring in a particular direction? So what do we know from our experience? Is our force have to get bigger, smaller, or stay the same as I try to pull this spring away from its natural or equilibrium position? What do we know?
The force would have to be more.
And force gets bigger, that's right. So the further and further and further I pull this thing away, as we can see down here with the applied force, the force at which I have to apply has to get bigger. So one thing this tells me is that the further I displace it away from its equilibrium position, the greater that this force becomes. Well, what about if I compress it instead, if I go the other way? So if I go back to its equilibrium position and then I start to compress it, what happens in that case? Does the force get bigger or smaller? Do I have to apply more or less force to compress the spring?
Apply more.
I have to apply more, exactly. So I have to push it further and further and further, or harder and harder and harder to get that thing to move further and further away from its equilibrium position. That's right. Good. So what that tells me then is, let's go back to here, we have what's known as Hooke's law. So what Hooke's law says is that this force I have to apply on the spring, which is the same as the force that the spring is applying, then is proportional to the displacement, right? Where x here is going to be the displacement. So the displacement in this case is the distance away from equilibrium. And I'm counting equilibrium here as x is equal to 0. equilibrium. So in this case, we're setting the equilibrium position at equals to 0. So wherever that origin happens to be. Now the other thing I'm going to do, so let's go back to our simulation here, is what? What also happens to the force? So let's go back to here and bring it back to its equilibrium position. And let's look at the equilibrium position and the displacement. So here I have a particular spring. This has particular what's known as spring constant. So if I pull it, I can pull it fairly far with this particular spring constant. So up to 100 newtons. But if I instead bring this back to equilibrium, and then I increase the spring constant here, so let's jump it up by a lot. And again, I grab the same spring and I try to pull it up to now the same 100 newtons. I can't displace it basically as far. So here, there's a proportionality factor which goes between here, which is what's known as the spring constant. So what Hooke's law actually says is that the force supplied by the spring is equal to negative of K, where K is what's known as the spring constant, times this displacement. So K here is what's known as the spring constant. So the spring constant is a constant proportionality which goes between the force and the displacement, which basically tells you how does the force grow. So what this thing actually says is that the longer or the larger the spring constant is, the greater amount of force I need for that amount of displacement at which I move it. So the spring constant is exactly that. It's simply a constant. It's a constant which only depends on the material of the spring. So the spring constant here only depends on the material, which basically means that it doesn't matter how far I move it. All it depends on is the type of material at which it is that I want to move. So some springs are going to have small spring constants. For example, if you think about a clicky pen, so in that case, if you click your pen, that's going to have a very small spring constant because it doesn't take a lot of force to move that by a large distance. But if you thought about your car, the shock on your car, that thing has a very large spring constant because when I get into it, I don't want it to drop down or to move a lot when I actually get inside of the car. So this is what we call Hooke's law. So again, Hooke's law says that again, as I move my object away from its equilibrium, it's going to feel a force, and that force is going to be back towards its equilibrium position. That's what this negative sign here means. So this negative sign here means that the type of force that we're dealing with is what's known as a restorative force. So the restorative force basically means that it always wants to go back to equilibrium. This is not writing very there we go, equilibrium. Great. I look like a third grader when I'm writing. Okay, so anyways, that restorative force, that negative sign is the key part here. So that negative means that the force is always in the opposite of the direction of the displacement. So again, let's go back to our simulation. So what that means is, again, if I bring this thing back to equilibrium, so where's equilibrium? Let's just do this. Okay. So when I grab onto this, if I turn on the spring force and applied force, in this case, I'm applying a force to the right, but the spring itself is pulling it back to its equilibrium position. So as I displace it, any positive displacement I have, meaning anything that I displace it to the right, the force then will be to the left, wanting to bring it back to its equilibrium position. Now, if I go past equilibrium and I push it to the left, meaning I'm now giving it a negative displacement, the force now will be to the right, trying to push it back to its equilibrium position. So Hooke's law, or anything which satisfies simple harmonic oscillation or simple harmonic motion, is some sort of restorative force. There always has to be something which wants to pull it back to its equilibrium position. So for the spring mass system, it is simply the spring itself. The spring wants to always go back to its equilibrium position, which makes it a restorative force. For example, with my keys, when I displace this away from the vertical line here, this thing also has a restorative force, where that restorative force is actually gravity. So as this thing moves off to the side, gravity's trying to pull it down, which is causing it to move back to its equilibrium position. So with the moon, it's actually gravitational. That force is the gravitational force, which is trying to pull it into the center of the Earth. But that thing is constantly moving due to its tangential velocity at which it has. So Hooke's law, which satisfies for, again, anything which is moving under simple harmonic motion, has to be some sort of restorative force. There has to be something which is pulling our system back to equilibrium, which again is the point of this negative sign here. So the negative sign tells us that this thing has to be some sort of restorative force. So let's think about the motion. What type of motion do I actually get out of a restorative force? So let's go to this simulation, and let's say here I have a vertical spring, and I'm going to attach a mass to this guy. And let's watch this and kind of see what happens. So first thing is first, I'm going to grab this guy and I'm going to pull it down. So again, when this thing is simply here, we're going to call this position here, this is its equilibrium position. So this is where the whole system is at static equilibrium. So I'm going to pull it some distance down away, some maximum distance, which is what we call the amplitude. And then I'm going to let it go. So what happens? Well, what we know is, again, as I pull this thing away from its equilibrium position, the force is increasing as this thing is moving further and further away. Let me stop this and pull it back. So the further and further I pull this thing away from its equilibrium position, the greater and greater the force becomes. Okay? But Newton's second law tells us that what? If the force is becoming greater, the acceleration is also becoming greater. So as I grab this guy and I pull it, the further and further I pull this thing away, the greater and greater the amount of acceleration becomes. Now, when I let it go, what happens? So initially it has zero velocity, but it has the greatest amount of acceleration because it is displaced the furthest away from its equilibrium position. So when I let it go, the velocity then starts to increase, but as it starts getting closer and closer and closer to its equilibrium position, the acceleration is getting smaller, but the velocity is getting bigger. So by the time it gets to its equilibrium position here, let me stop it when it reaches there. What happens is that the acceleration goes to zero, but it reaches maximum velocity. So the point of, as it's moving up, it now has maximum velocity at its equilibrium position with zero acceleration, which means there's nothing to stop it. So it has too much momentum now, so it's going to carry on past that equilibrium position and keep going throughout its oscillation. Now, as it moves away, the acceleration now is going to point in the opposite direction. It's going to start to slow down because as it moves further and further away, the acceleration is getting greater and greater and greater and greater, which means that the velocity is getting smaller and smaller and smaller until it reaches its maximum displacement on this side where it momentarily stops. Now, the acceleration and the force is now towards the center, which causes it to increase its velocity, decrease the acceleration, causing it to reach the equilibrium with maximum velocity again. Zero acceleration, nothing to stop it, so it overshoots, which is what causes the harmonic oscillation. So this all has to do, again, with this restoring force, that the force always goes back to equilibrium, but it's directly proportional to the distance it is away. So let's see how that works. So let's go talk about Newton's second law. So let's say here's my spring mass system. So here's my spring attached to my mass. And let's say, actually, I'm going to draw this horizontally. So let's do a horizontal just to make it a little bit easier. Great. So there's my mass, there's my spring mass, and let's say here's my equilibrium position. So this is my x is equal to 0. And I displace this thing by an amount of x. Okay. You should stop doing that. Great. So let's then think about the sum of the forces. So Newton's second law says that the sum of the forces then acting on my object must be equal to the mass times the acceleration. Now here, the only force which is actually acting on this, if I displace it to the right, is the spring force, which is actually pulling on it in this direction. Right? So this is going to be the direction of my spring force. So this says that the only force acting on it is my spring force, which is equal to the mass times the acceleration. And we now know that this is equal to minus k times x, which is then equal to the mass times the acceleration. So if we solve this for the acceleration, this says that the acceleration then is equal to negative k divided by m times the displacement. So again, we can see that the acceleration that this thing has, again, while it is actually oscillating, if I pull this, is again directly proportional to the distance at which it is away from the equilibrium. So as this thing is oscillating, again, as it moves further and further away, the size of the acceleration gets bigger and bigger, and then as it moves closer, the acceleration gets smaller and smaller. So what that ultimately tells us then is that what? This acceleration is both position and time dependent. So this is a position and time dependent acceleration, because the position is time dependent. So that means that this acceleration is also going to be time dependent. Now, what does that mean? So that means if we have a position which is, or an acceleration which is position or time dependent, can we use kinematics to actually describe the motion of this object? So if I wanted to talk about the position at which this thing was as a function of time, could I use kinematics to describe the motion of this oscillator? So what do you think? So think about 175. What did you learn in 175? So if we have an acceleration which is time dependent, can you use kinematics to talk about its motion?
Do we just use one of the laws of kinematics, or the kinematic equations that have time as a variable?
Well, so let's write down our kinematics. So let's go back to our kinematics. So we have V is equal to V naught plus A times T. We have X is equal to X naught plus V naught times T plus 1/2 AT squared. And we also have V squared was equal to V initial squared plus twice of A times delta X. Good. So you're saying we could use either the first one or the second one here?
Sure.
Sounds good. So who was talking? Was that Callie?
Yes, Callie.
Great. Okay. So how many agree with Callie? Usually I'd make you guys raise your hand in class, but I can't really. Everybody doesn't want to be viewed. Nobody wants to show their lovely faces. So I guess I'll have to do an aye or nay or whatever. So how many of you agree with Callie? So could we use, say, equation 1 or 2 here to describe the motion of this harmonic oscillator, given the fact that the acceleration is position and time dependent? So what do you think? Who wants to agree?
I'll agree with her.
Yeah.
I'll agree with her. It's a 50-50 shot. I'll do it.
That's good logic.
We love it.
I agree too.
I'm sorry?
I agree with her too.
Okay. So how many don't want to agree? Anybody want to go against what Callie said?
We'll go down together, guys. It's okay.
Solidarity. Sounds good. Okay. The answer is actually no, we can't. And the reason for that is, remember, the big stipulation about using kinematic equations was that this acceleration had to be constant. So wherever this acceleration shows up means that it has to be a constant. So for this to be true, this acceleration here, and this acceleration here must all be simply a constant, which means it has to be non-time dependent. It just has to be a number. Something like gravity, right? The acceleration due to gravity we know is 9.8 meters per second squared, which is a constant on average everywhere across the surface of the Earth, so we could use these kinematic equations. But here, because this acceleration is non-time dependent, it is time dependent, means that we can't use kinematics. So to describe the motion of this harmonic oscillator, we actually can't use kinematic equations. We have to use something else. Now, let's also go back to 175. So, especially those recently in 175. if you came into a position where you couldn't use kinematics, what did we have to use instead? So what was the big concept that we used to talk about the motion of an object if we couldn't use kinematic equations?
Was it energy?
Energy, fantastic. That's right. So here we can actually talk about energy. So let's talk about the energy of a harmonic oscillator. So first things first is we know that what? So let's go back. We know that total energy of our system is always going to be kinetic energy plus, how did you guys write potential energy? Just PE or U, or what did you call it?
We used PE.
PE? Great.
Mhm.
Okay. I might default to something else later, just remind me. Okay. So here we can say the total energy then of our harmonic oscillator then is going to be what? Kinetic energy and then potential energy. So does anybody remember what kinetic energy is by definition?
Is it 1/2 mv squared?
Fantastic, good job. So it's 1/2 mv squared. Good. So all this thing says is that what? It's a scalar quantity, no matter what direction it's moving, all that matters is it has a velocity and a mass, and then whatever direction it's moving, as long as those things are the same, it has the same kinetic energy. Good. And then here, this is going to be the potential energy of a spring. Does anybody remember the potential energy of a spring?
One half mgh?
1/2 is
no,
correct.
no, that's just potential. No, that's wrong.
Good. Yeah, mgh, that's a gravitational potential energy. So close. The 1/2 is right. I'll give you a hint. It has a spring constant in it. There we go. So it's 1/2 kx squared. So it's 1/2 the spring constant times the position squared. So good. So here we can talk about its motion, again, using this energy. So now it turns out that for most harmonic oscillators, so again, for example, my keys here, again, if I lived in a vacuum, which I don't, which is good because otherwise I'd die, there is some sort of friction, right? So this thing is moving in a fluid, there's friction in the fluid, but you know, let's pretend that there is no friction and pretend there's no friction up here. So again, as this thing actually oscillates back and forth, as long as there's no friction, what's true is that the total energy of this harmonic oscillator is constant. So this has constant energy to it. So this total energy must be the same at all points along its trajectory. So all that means is if we think about our horizontal springs, let's say here's my spring with my mass, right? Let's say here's equilibrium position. So this thing, say, is moving this way with initial velocity. And if it's, say, here, so it's stretched a little bit further, so let's say now it has a small velocity, but it has a much bigger displacement. What has to be true is that the total energy here is exactly the same as the total energy here. So as long as there is no friction present, the total energy within inside of our harmonic oscillator is simply a constant. It's the same at all points. The only thing that's going to be different is, again, here, this has a much smaller displacement with a much larger velocity. But here, this one has a much larger displacement with a smaller velocity. So as this thing is moving throughout its harmonic oscillation, let me go back to here. Again, as I pull this thing, what's happened is that at any point along this trajectory, the total energy is constant. It stays exactly the same. But what's changing is the potential energy and the kinetic energy. Now, let's go back to what we talked about before. So here what we know is by the time it reaches its maximum displacement, this position here, this thing then has what? 0 velocity. It momentarily stops, which means that the total energy at this point is simply potential energy. Then as it moves up, the potential energy is decreasing, the kinetic energy is increasing until it reaches its equilibrium position, where at that point we know it has 0 displacement, so it has 0 potential energy, but it has then all kinetic energy. So at these two extremums, so at its maximum displacement and at 0 displacement, it has a total energy which is only defined by either its potential energy or its kinetic energy, which we can use then to determine the total energy of our system. So let's write all that down. So what we know then is at x is equal to 0, in this case, we know that what? V is equal to the maximum velocity. We know the acceleration is equal to 0. And we know then that the system, the total energy then, is going to equal only kinetic energy. So it's going to have the maximum amount of kinetic energy. Simultaneously, at x is equal to the max displacement, oops, which is what we call A, which is the amplitude. So the maximum displacement this thing has is called the amplitude. In this case, we know the velocity then is equal to 0. The acceleration is equal to the maximum acceleration, which means the total energy then is equal to purely potential energy. So this is going to be the maximum potential energy. So let's go back to here. So what this means then is that the total energy then is going to be equal to 1/2 the mass times its maximum velocity squared. And then down here, we're going to have that the total energy then is going to be 1/2 k times the amplitude squared. Now, typically, what we're going to know is, again, the displacement at which I move something. So if I pull out this ruler here, and I put this at the equilibrium position, then what I would know is I originally displaced this thing about 45 to the top, so about 35 centimeters, right? So that's the initial displacement, which in this case would be the amplitude. So that maximum displacement at which I pull this thing, which again is what we call the amplitude, typically I'm going to know that, so it's much easier for me to write the total energy than as simply 1/2 k times that amplitude squared. So typically we're going to write the total energy then as 1/2 k times that amplitude squared. So what conservation of energy tells us then is that what? The energy the harmonic oscillator has at any point has to be constant, which is simply equal to 1/2 k times the amplitude squared, or if I write it down here, 1/2 m times v max squared equal to 1/2 mv squared plus 1/2 kx squared. This is also true if I know that initial velocity. But that has to be constant. So this has to be equal to the total kinetic energy and then the total potential energy basically at any point. So what this thing says then is what? If I know the amplitude and I know the spring constant, then I know the total energy. And then when I'm looking at something like a given displacement, I can then determine exactly what the velocity is if I know the displacement. Or conversely, if I know the velocity at any given point, then I can determine exactly where it is, i.e. what its displacement is. So conservation of energy, just like you've seen before, allows you to be able to describe exactly what this thing is doing, but I have to know certain things. So again, I have to know the amplitude or the maximum velocity, I have to know the spring constant or the mass, and I have to know either how fast it's going to determine where it is, or where it is to determine how fast it's going. So this will allow me then to determine certain things. For example, one thing it'll allow me to determine is what is the maximum velocity at which this harmonic oscillator can move. So again, let's say that I know the total energy, which is 1/2 kx squared, and I want to know what is the maximum velocity. So in this case, this has to have maximum kinetic energy, meaning that it's at the origin, so x has to be equal to 0, which then has to be 1/2 m times v max squared. So if I want to know what is the maximum velocity at which my harmonic oscillator can have, again, when this thing reaches the equilibrium position, that's where it's going to have its maximum amount of velocity, then we can simply solve this expression. So here the 1/2s are the same, so we can cancel those out. So this says then that what? The maximum velocity is going to be equal to k divided by m square rooted all times the acceleration. So this is the, or sorry, not acceleration, the amplitude. So this is the maximum velocity at which my harmonic oscillator can achieve. So things I should probably tell you as I'm working through examples, which we'll do some in a little bit, I will pretty much always do everything algebraically and then throw in my numbers at the end. And one thing I tend to do a lot is skip about 100 steps in my algebra. So anytime that you get lost on what I did, please stop me, backtrack me, slow me down, Anything that you need to do, like I said, I tend to skip steps. So again, if there's something that I did that you don't understand what I did, just definitely backtrack what I did, okay? Good, so this is then the maximum velocity at which this thing can achieve. But let's say, so again, one thing about conservation of energy though that we lose is, remember, energy doesn't tell you anything about things like what? Time. So this is great and all. I mean, you could tell you exactly where it is given how fast it was going, or how fast it's going given where it is. But if you want to know exactly what that thing is going to be at a moment of time, so either how fast it's going at a moment of time or where it is at a moment of time, conservation of energy is not going to work. So we still need to know, how do we describe its position as a function of time? How would we actually do this? Now, in a mathematical sense, we would actually have to go beyond calculus to do this. So calculus actually wouldn't even work for us. We'd have to use what's known as differential equations. But since that is definitely not a requisite for this course, we're not going to do that. So what we're going to do instead is we're going to go back to our simulation here, and we're going to simply watch it. So if we watch the motion of this, this will actually give us a lot of information, and it will actually hypnotize the chicken. So great, so let's talk about this. So let's say, again, I'm gonna pull this thing and I'm gonna hold it here, and let's say this is time is equal to 0. So I'm gonna displace it to an initial displacement of 40 centimeters, and I'm gonna let it go. Now imagine on the mass here, I put a pen, so like a pen here, and I'm gonna attach that to my 50-gram mass, and I'm gonna have this draw on paper, and then let's say I'm gonna pull paper to the left, okay? So as this thing actually starts to oscillate, so my pen is drawing a line, basically oscillating up and down, but my paper is being pulled in this direction, and I want to think about the shape that this thing is actually drawing. So what type of curve would I get if I plotted, for example, position along the vertical axis and then time along the horizontal axis? So again, I have my pen attached to my harmonic oscillator. This thing is just drawing a line straight up and down. Right? So it's going from 40 centimeters up to minus 40 centimeters, back to 40 centimeters, and along the way. But I have paper which is being pulled to the left at a constant rate. So what type of curve would show up then on my plot here? What would that look like?
Like waves, like parabolas. Maybe.
What do you mean by waves and parabolas? Those are almost two different things. I think you're on the right track, but what do you think?
Is it like a sine wave?
It's like a sine wave. That's right. I think that's what you meant by waves. Exactly. It would look like a sine wave. Now, in this case, it started off at maximum displacement. So I'm going to call that maximum displacement up here A, which again is going to be amplitude. And then goes down here to minus the amplitude. So exactly, this thing is going to start off here, and it's just going to do something like this, right? That's a horrible drawn curve, but hopefully you understand what I mean. so that's right. So here, this maximum displacement, again, this is our amplitude. So this is the maximum displacement it's going to have. So it's going to draw out a sine or cosine curve or something like that, which is going to look something like this. That's right. So here, what this means then is that if we wanted to write down a description of our harmonic oscillator as a function of time, this thing is going to go as x of t is equal to a, where a is that amplitude, which just tells me how high that thing is, times then cosine of what we call omega t times time, where omega here is now what's known as the angular frequency. Now, you saw omega before in 175. That's what you call the angular velocity. Well, this time it is what we call angular frequency. Turns out it's actually relatively the same thing, and we'll see that in just a second. This thing is actually related to the frequency, so in exactly the same way as the angular frequency or the angular velocity. So 2 pi times the frequency is then equal to the angular frequency. This is typically my f. But if you want, I can always write f this way. Which f do you prefer?
The second one, please.
The second one? Okay. I'll try to remember to do that. Okay. Let me make a note. Remember. Okay.
I have a quick question.
Sure.
The amplitude values on the y-axis,
Yes.
they're both negative. Can you just explain why that is?
Oh, no, one was supposed to be positive, the other one is negative. So sorry about that. I think the second one showed up as negative when I tried to cross my T here.
Oh, I see. Okay. All
So
good.
yeah, let me redraw it here. So yeah, this one should be positive A. This one should be negative A. That's right. Yeah. And it should do, let's see if I can draw it prettier. There we go. It's a little bit prettier. There we go. How's that? Not too bad. Okay. No. So yeah, so the one is positive and the other one is negative. Yeah. And that just depends on how I define my system. So for example, here, if I call going downward as positive, then this would be my positive amplitude, and then this one up here would be my negative amplitude. But just depends on how you define your system. So, yeah, sorry about that. And remember also from uniform circular motion that frequency is related to period inversely, where period here is the amount of time it takes to go from the amplitude back to the amplitude. So this time section from here to here is what we call the period. So the period then is the amount of time it takes for this thing to go through one full oscillation. So again, if I go back to my simulation here, so again, if I pull this thing to, again, let's call that 40 centimeters and I let it go, the period then is the amount of time it takes to go from positive 40 to negative 40 and back to positive 40. So for example, if I pull out the stopwatch, so let's get it down here. Then that would take about 0.54 seconds. So this would be its period. So the period of oscillation in this case then would be that amount. So the period is the amount of time it takes to go through one full oscillation. So let's talk about more this angular frequency. So the angular frequency, like I said, is actually related to the angular velocity. So this is actually very similar to angular velocity. So let me write this in green. So this is similar to angular velocity. So next part is then I'm going to try to convince you of that. The way I'm going to do that is I'm going to pull out this other simulation here. And so let me stop this one for now. So this is a bug on a rotating platform. So simply all I'm going to do is I'm going to move this guy down here. Okay, so this guy's going to be sitting here. Let's show the acceleration, and I'm going to put this with an angular velocity. Okay. So now I'm going to pull this guy down here. So he's about the same height. That should be about good. Okay, so next time he reaches to the bottom, we'll put this and then we'll just watch what happens. So not perfect, but about the same. Maybe if I brought that up to 81, that might be a little bit better. Okay, so let's try that extend. Reset all, bring you back down here. And at 81. Okay, let's try that one more time. So what this basically shows is that the harmonic oscillation of the spring mass system going up and down versus the bug here rotating in a circle is the same. Which basically means that if I took this platform and I rotated it and I only looked at the side, what you would see is that the bug would actually be undergoing harmonic oscillation simply up and down, even though it's actually moving in a circle. But if I look at it from the profile, from the circle, it actually just looks like it's moving up and down. So the reason that the angular frequency then is related to the angular velocity is because if I simply took this bug rotating in a circle, turned it sideways, it would look like it's simply moving up and down. So let's draw that over here. So basically what that means then is if I had a circle, so here's my circle, here's my point on the circle, this thing is experiencing a centripetal acceleration towards the center. So if I define this angle here, what's happening then is we're watching this vertical position here, so we're only seeing how this y portion across here is actually changing. So what we know from uniform circular motion is that centripetal acceleration is equal to negative, due to the fact that it points towards the center, times the angular velocity squared times then the radius. Right? This is what we remember from centripetal acceleration. But here I'm only looking at the y portion of that. So for the y portion, I would then say, well, the y portion of the acceleration then would be negative angular acceleration times y. But the y portion here, according to this angle, then would be what? So this would be the adjacent side of that angle, which means that would be the cosine portion. So here, this would then be what? So for the y, I'd have y then would be equal to the radius of this, which I'm going to simply call the amplitude, times then cosine of the angle, let's call that angle theta. But since this thing is moving with a constant angular velocity, say in this direction of omega, then we know theta then is equal to omega times t. So this thing is going to be equal then to what? A times cosine of omega t. So even though here, this happens to be the angular velocity, it's related back to this angular frequency, but because again, if I took something which was rotating in a circle with a constant angular velocity and I simply turned it sideways, I couldn't tell the difference between this thing simply moving in a circle versus something moving straight up and down. They look exactly the same. So this angular frequency, even though it's talking about a frequency of something moving up and down as opposed to something moving in a circle, but it's intimately related to this angular velocity because it has exactly the same meaning to it. It's something which is constant. It's something which depends only on the velocity at which this thing is actually moving around. Now, this portion here, this is actually an extremely helpful portion. And what this actually tells me is how I can actually determine what is the angular frequency of any harmonic system. So again, if we go all the way back to our spring mass system that we wrote down here, what this statement basically says, let me go back to here, not to make you all dizzy, is that the acceleration is equal to minus the angular frequency squared times then the position. So if I go back to what I wrote down before for the acceleration, what we said is that the acceleration then was equal to minus k divided by m times the position. Now if I compare this then with that centripetal acceleration, which was equal to minus omega squared times, let's call it x in this case because we're not doing the y portion, all I have to do then is read off of whatever's in front of the x with that negative sign is then going to be the angular frequency squared. So if I go back to my spring mass system, so if I draw my spring mass system, what I know again is that the acceleration is equal to negative k divided by m times x. If I compare that then to this value here, what we can imply then is that what? The angular frequency must be equal to the square root of k divided by m. This is true for any type of harmonic system. And we're going to see this when we start talking about pendulums. So when we talk about a pendulum, to know the angular frequency of this pendulum, i.e. how this thing actually oscillates about the frequency and the period and etc. Because again, if I know the angular frequency, I know the frequency. And if I know the frequency, I know the period. Then I can determine the period of oscillation of this thing by simply knowing what is that angular frequency. And the way we determine what that angular frequency is we have to draw the forces acting on the object. From those forces, we isolate the acceleration, which is what, again, we did here. So once we isolate that acceleration, then whatever shows up in front of the x is the angular frequency squared by definition. So this is how we actually determine what is that angular frequency. Now, if we go back to then what we wrote down for the maximum velocity, so from here, we had the maximum velocity. Where was it? Maximum velocity was equal to the square root of k over m times the amplitude. Well, again, compare that to what we just wrote down, then that is going to be the angular frequency times the amplitude. So what this says then is that the maximum velocity is actually equal to the angular frequency times then the amplitude. So let's kind of recap all these things that we just talked about. So for a simple harmonic oscillator, what we now know is that what the position as a function of time is equal to the amplitude times cosine of omega t. I'm going to change that in just a second. We now know that the acceleration is equal to minus the angular frequency squared times the position. We know the maximum acceleration is then going to be when the position is at the amplitude, so it's going to be the angular frequency squared times the amplitude. And we now know that the maximum velocity is going to be the angular frequency times that amplitude. These things are true for any harmonic oscillator. Doesn't matter if it's a spring mass system, or if it is a pendulum, or if it's the moon orbiting the Earth, or if it is an atom inside of a lattice. These quantities are the same for any harmonic oscillator. This is actually quite beautiful. What changes, though, is this value. What did I do? Of omega. Omega, would you stop that? Oh, because I'm using the wrong end. Okay. So omega will be different for any type of one of those different systems. What we have seen now is that for a spring mass system, as long as I have one spring with one mass, omega then is equal to the square root of k over m. So if I'm dealing with a spring mass system, automatically I know this omega based off of the properties of what's going on. So this only depends on the spring constant. It only depends on the mass which is attached to it, which then tells me exactly what this is, what this is, what this is, and what this is. So again, these are general. These ones here that we wrote down, these are general for all situations. This here, though, is very specific. This is only specific to a spring mass system. As I have different systems, the angular frequency will be different for each one of those different systems. And this is what we're going to kind of work on over the next couple of days, seeing what types of different omegas that we have for different types of systems. Is everyone okay with this? I know it's kind of a lot. A little bit of a leap of faith at this stage. Is everyone okay?
I have a question.
Sure.
So the point, I don't mean to say it like it's about to come out, but the point of all of this was because we needed something where we could do the position as a function of time.
Mhm.
Okay.
That's right. So that was what all of this argument was. That's right. And then the next part was to basically show that it is very similar to a uniform circular motion to be able to drag out what the angular frequency is. So that was the main point of all this. So the whole entire point of this page was to basically drag out omega. So we want to see how do we actually determine what omega is based off the fact that we can make an analogy between our spring mass system and something moving in uniform circular motion.
Okay.
So now for any system that is moving in uniform circular motion, we now know how to pull out that omega. And we're going to see how to do that over some more examples, not today, but probably starting tomorrow. Is that okay?
Okay.
Okay.
Yeah.
Good. Is everybody else okay?
Yep.
Good. Okay. Okay. So let's go back just a second. So now what I wrote down here as x of t is equal to a cosine of omega t, that's only true in that initial scenario that we showed down. So again, if I took this thing and I pulled it to its maximum amplitude and I let it go, well, yes, it's a cosine curve in this case. But what would happen if, for example, so let's bring it back to its equilibrium position, if instead of me pulling it and letting it go, I gave it an initial velocity downward instead. So let's say initially this thing was at equilibrium. I didn't like that mass being there, so I kicked it. Screw you, mass. And this thing starts to then harmonically oscillate. Well, this thing wouldn't fit a cosine curve anymore because now it's not going to be at its maximum displacement like here, but it would actually fit a sine curve in that case because now it would actually start off here and then end up doing something like this, right? So, or it could be something in between. I could start it off at a particular position with an initial velocity. So that position we wrote as a function of time is only true in one scenario. So in general, what we usually write down is that x of t is equal to the amplitude times cosine of omega t plus what we call phi. Phi here is what's known as the phase factor. So what's the phase factor? So the phase factor simply tells me where does my system start at the initial time. So this is information about the starting position and velocity of our harmonic oscillator. Okay, so for example, I have these three plots here. So each one of these has exactly the same amplitude. So they all have 2, whatever 2 is, say 2 centimeters or 2 meters or whatever. They all have exactly the same angular frequency, but they all start off differently. So the blue curve here actually has, this is a cosine curve. The what's that orange one here, this one is displaced from him by 45 degrees. And then the green one here, this one is actually a sine curve, which is displaced from the cosine curve by negative pi over 2. So what the phase factor basically tells me is how does my harmonic oscillator start at the initial time of t is equal to 0. From that point on, the phase factor stays constant all the time. It is not dependent on time, it doesn't change, it doesn't do anything. The only thing it basically tells me is where does this thing actually start. But everything else is determined, for example, the period, the frequency, the amplitude, all of that stuff is exactly the same because the amount of time it takes to go from this crest to this crest is still the same time it takes to go from here to here, which is still the same time it takes to go from here to here. But again, all the phase factor tells me is how this thing is behaving at time is equal to 0. So again, this is information about the starting position and velocity, i.e., what's happening at t is equal to 0. But again, this thing is simply constant. It stays fixed at all times. So the phase factor, again, tells me the last bit of information I need to know. Is this thing a cosine curve? Is it a sine curve? Is it something in between? What is this thing doing at the initial time? Did I pull it to maximum amplitude and let it simply oscillate? Or was it at equilibrium position and I simply kicked it, gave it an initial velocity? Or did I pull it out a particular direction and push it to give it some initial velocity and some initial position? So this is what the phase factor tells me. So in general, when we write down the position as a function of time, this is what we actually write down. So we need to know exactly what is that phase factor, which again, that phase factor is determined by simply the initial conditions of our system. Once we know that, we'll determine that phase factor, and then we can just write down everything else, which now only depends on the angular frequency and that amplitude. Now, we're out of time for today, so we'll see how to actually do that tomorrow. So we'll do some examples of how do we determine the angular, phase factor, how to determine the angular frequency, and then we'll do a couple examples first thing starting tomorrow, and then I'll have you guys start working on some group assignments from there. So any questions about anything that we talked about today? Again, I know it's kind of a lot. It's always a lot on the first day, but again, it takes a little bit of a leap of faith to be able to go from harmonic oscillation to uniform circular motion. But again, as Callie was asking, the main part of this here is to basically get to this. So to see how these two things are related. So as long as I know how these things are related, anytime I wrote down some of my forces, I can then extract what this angular frequency is. Once I know that angular frequency, I can now use these expressions, because all of these expressions are general for any type of harmonic oscillation. They're only dependent on this angular frequency. So once I know that angular frequency, which I get by the physical parameters of the question, or at least the physical properties of what this thing is actually doing, then we know everything about our system. Okay? And again, we'll see this over the next day or so, a little bit more, give you some more concrete example of how this actually works. So, is everyone okay? Any questions at this stage?
Do you recommend, how close, I guess, I mean, obviously reading the book is probably a good idea, but is it worth the time to like read the entire chapter and, you know what I mean? Like, or is there another way you recommend to study and review the day's notes?
Good question. Who's talking at the moment? I can't see.
Callie.
Oh, Kelly again. Okay. Hi, Kelly.
Hello.
Good. So I always teach under the assumption that you're never going to open the book. I don't know how accurate that is. I always find it to be somewhat accurate. So I'll give you basically as much information as possible. Of course, yes, reading the chapter is always good. Otherwise, you know, there's plenty of, you know, YouTube stuff. You can always go get somebody else's opinion by watching other YouTube videos, for example. So now when you mention studying, what do you mean, getting ready for the exams?
Just, I think daily, like, I feel like with this fast-paced course, it's all going to be getting ready for the exam since we're going to have one basically every week. So it's kind of like the same to me, but.
Right. Basically, so what I would say is, I mean, a good thing to do would be, as we go over material for that day, you know, sit down and maybe do 1 or 2 of the homework questions that I put up. All of the ones for chapter 11 are already on there. So, I mean, it's a good way to kind of test how you're doing, as well as with the conceptual questions, you know, kind of see where your conceptual and your mathematical, you know, kind of are kind of sitting at the stage. Yeah, after that, like I said, yeah, just kind of re-going through what it is that we talked about, make sure that everything actually makes sense. Things that don't make sense, either, you know, talk to me, make an appointment with me, or like I said, you can read the chapter or watch some YouTube videos, because I'm sure somebody made hundreds of videos on harmonic oscillations and things like this. So,
All right. Sounds good. Thank you.
I don't know if that actually answered your question, but
No, it does. It does. It just helps me kind of funnel in what I need to focus on. So
yeah, like I said, I think, you know, the most important thing is basically just practice. Yeah, and so kind of sitting down, you know, after we're done, you know, so tonight at some point, maybe not tonight because we haven't actually done any example questions yet, but definitely tomorrow, you know, sometime tomorrow night, say, sit down and try a couple or a few of the ones that I posted online. So, you know, just kind of see how they go, you know, make sure that you kind of understand what's actually going on. So, yeah.
Sweet. Thank you.
You're welcome. Any other questions anybody has?
Are the conceptual questions already up on Mastering Physics?
The ones for today, no, not yet. The chapter 11 homework is up there, but conceptual questions I'll probably put up during the lab. And there was another question as well. Somebody else had another question.
I had the same exact question. So.
Oh, okay. Gotcha. Yeah, I was kind of debating whether I wanted to do conceptual questions today or not. I didn't quite know how far we would make it. That's why I didn't put them up yet. But I did post the chapter 11, you know, kind of practice problems there. But yeah, I'll probably post a few conceptual questions during the lab if nobody really has questions during the lab. If not, when I do post them, I will send out a message on Blackboard So that message will go to everybody so that way you know when they're actually posted. So it won't be a surprise. I'll do that every time. It got really hot in this room. Okay. Any other questions anybody has? No, it was okay. All right. Well, in that case, then I will see, I think most of you in lab. We'll talk about some lab stuff and then kind of go from there. So I'll see most of you then in what? 7 minutes, right? 6 minutes? 8 minutes? Something like that.